Hi Algebra 1 students, this is Miss Graham, and today we are going to be starting a new unit. We're going to be looking at Unit 4, Exponents, Radicals, and Polynomials. So go ahead and pull out your physical or digital textbook and start off on page 287. We're going to have pages 287 through 290 out. We're going to look at lesson 19.1, Basic Exponent Properties. And this is within our section of learning about different exponent rules. Our learning targets for today are to develop basic exponent properties, and we're going to simplify expressions involving exponents. So let's go ahead and read the part below where it says, an iceberg is a large piece of freshwater ice that is broken off from a glacier or ice shelf and is floating in open seawater. Icebergs are classified by size. The smallest size iceberg is called a growler. A growler was found floating in the ocean just off the shore of Greenland. Its volume above water was approximately 27 cubic meters. So now looking at this, we're going to see how this real life situation is going to apply to looking at exponents and exponent rules. So start thinking back to your math class last year and the time of year when you started looking at different exponents and being introduced to what they were. So below on number 1, it says, 2 icebergs float near this growler. One iceberg's volume is 3 to the 4th times greater than the growler. So that's how we say this expression right there, that piece, 3 to the 4th power. Now, if we keep reading on, it says the second iceberg's volume is 2 to the 8th power times greater than the growler. Which iceberg has the larger volume? And it asks for you to explain. Now, this is something where we're going to start to look at how we could use our calculator or even thinking of what exponents represents with these different pieces. Let's start off looking at 3 to the 4th power. 3 to the 4th power is really saying I'm multiplying this number out this many times. So I'm multiplying the number 3 4 times. So we're saying we multiply 3 4 times. That's what we're looking for. Now, when we look at 2 to the 8th, we're saying we multiply 2 out 8 times. So I have 2 times 2 times 2. Oh my goodness. I only have 4 2s so far. 5, 6, 7, 8. Let's just double check. Yep. So that's where we multiply 2 8 times. So this is where we really need to pull out our calculator and compare these two numbers that we're actually looking at, right? We need to compare what we get. So we multiply 3 times 3 times 3 times 3. What we end up getting is 81. So I end up getting 81. When we do 2 times 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 2, oh my goodness, quite a tongue twister, we actually end up getting 256. So we know that 2 to the 8th is going to be greater than 3 to the 4th. So I could probably write the expression above. 2 to the 8th, let's try that 8 again. 2 to the 8th is greater than 3 to the 4th. Since we know 256 is greater than 81. So that's what I would probably say. I would say we know 2 to the 8th is greater than 3 to the 4th since 256 is greater than 81. So this part kind of, up here, this is our explanation. So which iceberg has the larger volume? And that's really our explanation. Whereas this part down here, this is kind of like the work that's required. Now, I know this semester we're really going to be assessing your knowledge of what you know, what you can showcase, so it's important that you show that work, especially when you're doing your homework as well. Now, what we did up in the work section in number 1 is actually going to carry over into number 2, because it's asking what is the meaning of 3 to the 4th and what is the meaning of 2 to the 8th, right? That's what it shows. It shows that, we can write out how many times we're multiplying a certain number. That's what it tells us. So it tells us how many times we multiply out a certain number. Now, what's cool about this, and what some of you might know, is why exponents are used when writing numbers. And that's what we're going to talk about. That's something you might see on your calculator as well. Exponents are actually going to make it easier to represent different products of repeated factors, right? Instead of writing out 2 so many times we're multiplying it, it's a simpler way to represent that. So I'm going to go ahead and make sure I answer the second part of the question, right? So where it says, why do you think exponents are used when writing numbers? We're going to say exponents make it easy. So exponents make it easy to represent products, right? That means we're multiplying. So products of repeated factors mean the same number that's getting multiplied over and over and over again. Now, we're also going to have an opportunity to see how we can put this in our calculator as well. So something to keep in mind. If you do want to read in the right side of the margin, there is a connection to geology about the iceberg, so you can go ahead and do that on your own time, but we're going to continue on below. So let's go ahead and look at number 3. It says, suppose the original growler's volume. So if we go back up, let's look at the original growler's volume. Okay, so I'm seeing, that it is 27, right? So it's 27 cubic meters. That's the original. So I'll write that in. That's the original growler's volume. So it's saying, suppose that we have that under the water. That part under the water is 9 times the volume above. So it's 27 cubic meters above. It's 9 times that volume below. So it says how much of its ice is below the surface. Well, we're going to take that 27, that was the original, cubic meters, and to get 9 times as much, right, it tells us exactly, let's multiply this by 9. So pull out our calculators, we type this on in, we get 243. So that means it's 243 cubic meters. So remember, we're looking at what the volume is below the surface. So the volume's quite a bit more, 9 times as much as the volume above. So now we're going to start to get into some different definitions if you go ahead and start looking at our margin on the right. So this is definitely where you want to have your highlighter out, where we're going to go through some math vocabulary, quite a couple different words that some of you might be familiar with. So right where it says math terms right here, we're going to read. It says the expression 3 to the 4th is a power. It says the base, so another vocab word, the base is 3 and the exponent is 4. Then it says the term power may also refer to the exponent. So really, there's kind of 2 definitions of power. So let's write down this 3 to the 4th example in the margin. So 3 to the 4th. So what we're going to do is we're going to label the base. So the number 3 is our base. So I'm going to try to use a different color to highlight what our base is. So in our previous problems, when we looked at, 2 to the 8th, the 2 would be the base. Now we're going to look at exponent. So exponent is going to refer to that kind of tiny small number that is raised to our base. So that's going to be our exponent. Now, a lot of times in mathematics, what they're saying is that this whole thing could be called a power, or they're saying the exponent can be called a power as well. I know sometimes it can differ per teacher. I know for me, I prefer to call the exponent a power, but just touch base with your teacher on the terminology that they like to use and prefer. So I usually stick with base here, and I usually stick with exponent and power here, even though this whole thing could be called a power. So something to keep in mind. So let's keep going below and read question number 4. It says, write your solution to number 3. Okay, all right, so write our solution as 243. It says using powers. Oh, okay, so it says complete the equation below. Write the missing term as a power of 3. So remember, power, we're looking at in this case is we're trying to use 3 as our base, and we're trying to figure out how we can write that down. So looking at this, all right, we can see that they rewrote the 9 that was up here as 3 halves. So let's just outline that so we can see that. They rewrote 9 as the same as 3 to the second. If I said 3 halves, I apologize. It should be 3 to the second. Because if we multiply 3 times 3, that's 9. So now what they want us to do is to figure out, okay, how can I write 27 with 3 as a base? What's going to be that exponent? So that's kind of what we're looking for. Well, it can't be 3 to the second, right? Because that's 9. What if I had 3 to the third? What would that be? So 3 times 3 is 9. 9 times 3 is 27. So you're right. So the exponent here would be 3. So it wants us to kind of fill in, okay, we know we're going to have 243 cubic meters, right? Because we just went through the process of how that's 27. We went through and said how this is 9. When we multiply those, we know we're going to get 243. But now we have to rewrite 243 using a base of 3. Okay, so we have 3, and we're trying to figure out what number is it going to be raised to. So maybe this is where you pull out your calculator, you're multiplying 3 over and over and over and over and over again, and, you're going to pause the video here, test it on out, and I want you to see how many times did you have to multiply 3 in order to get 243. So go ahead and try that out. All right. Did you get 5? Because that's what it should be. 5. So now let's look at number 5. It says, look at the equation you just completed in item 4. What relationship do you notice about the exponents on the left side of the equation and the exponents on the right? Well, let's take a look at this, okay? We see we have a 3, a 2, and a 5. Anybody notice a pattern? What can you do with 3 and 2 to get to 5? That's right. The exponent on the right side of the equation is the sum of the exponents on the left. So let's go ahead and we're going to write that in as our answer. So we're going to say the exponent on the right, so we're going to say 5, is the sum of the exponents on the left, which we know is 2 and 3. Awesome job. So we're starting to notice patterns. Maybe this is a rule that we're going to see, that when we have that same base and we're multiplying, maybe it will always follow through where we add the exponents. And we keep the same base. Let's go ahead and turn to page 288 to see what happens next. So number 6 says use the table below to help verify the pattern we noticed in item 5. So first it says write each product in the table in expanded form. So that's kind of a new vocab word for us here, expanded form. So down here, that means kind of like before, how we wrote, you know, each of the bases with the exponent, we wrote out how many bases there were. So looking at this, we can say we have 2 to the second, 2 to the fourth. I'm going to write out 2 to the second and 2 to the fourth. So 2 to the second, right? This is 2 to the second. This is 2 to the fourth. And then I'm going to try to convert it back into a single power. So I have 1, 2, 3, 4, 5, 6. So I have 6 2's I'm multiplying out. So that's why I now have 2 to the 6. We're going to go ahead and I'm going to pause. I want you to pause the video right here to go through and try to do the next one, because we're going to see if we can express, right, our expanded form as a single power. So I did the first one. Pause the video. Go ahead and do the second one now. All right, you should have your first cluster as 5 times 5 times 5. There is a multiplication symbol holding these together, so it should be times 5 times 5, because that's 5 to the second. All together, that means we have 5 to the fifth. So now I want you to pause the video, and I want you to try doing the same thing now, not with numbers as our base, but with variables. So go ahead, pause the video, and try the third one. All right, let's go ahead and look at this one. So I have x to the fourth, which is x times x times x. I'm multiplying times x to the seventh. X, all multiplied. All together, I see I have x to the 11th. Okay, let's try one last one. Go ahead, pause the video, try this one out, see what you get. All right, let's go ahead and see. We have a times a times a times a times a times a. That's a to the 6th. Then we're still multiplying times a, which is a to the 2nd. Altogether, it's a to the 8th. So, yes, you're probably looking at this and you're like, this is a little overkill. What's the pattern that we're recognizing when we're doing this, right? That's what number 7 is going to get us to do. So it says, based on the pattern we observed in the table from before, write the missing exponent in the box below to complete the product of powers property. So I'm going to go ahead and highlight that because that's another vocab that we're going to be looking at. But with this, if you're not necessarily sure about the names, that's fine. But I will tell you that these different exponent rules, they are things that you are going to continue to see on. Something you'll see, you know, in the next 2 years in Algebra 2 class. Something that you'll see also in beyond. So it's good for you to know that this is building the foundation to your mathematics learning. So focusing on this, let's say instead of, you know, numbers, we used letters. So think of the pattern of what you notice. What did we do every single time to get that final exponent? So what we did with the exponents, if we had the same base, that's what we noticed. Every time it was the same base, we kept the same base just like before, but we added the exponents. So what we can do now is we can write on in that it would be, and I'll zoom in a little bit. All right, there we go. We can write that it would be a to the m plus n. So we're using variables to show what we mean, but no matter what we do, when we multiply like bases, we add the exponents. So I'm going to write that off to the side. That's kind of the idea that we're looking at here. All right, so we're going to say when we multiply like bases, and when I say like bases, that means the same. When we multiply by the same base, like bases, we add the exponents. So when we multiply like bases, we add the exponents. That's going to be our first exponents rule that we are going to learn about. So what it wants us to do right now on number 8, it says, okay, use this rule we just learned, the product of powers property, to rewrite x to the 3/4 times x to the 5/4 as a single power. So remember what we learned up above, right? When we multiply like bases, right? When we multiply the like bases, what we can do is we can add the exponents. So we keep the same base and we can add the exponents. So we have 3/4 plus 5/4. hey, we know how to add fractions, right? We've seen this before, adding fractions with a common denominator. That means we can add the numbers together on top. So 3 plus 5 is 8. So we have x to the 8/4. But wait a minute, we can reduce that exponent, right? We can reduce 8/4 as 2. So once we multiply these two together, what we realize is we're able to get x to the second. Now, what we're going to do is we're going to skip numbers 9 through 11. We're going to go ahead and head to the next page, and we're going to explore what happens not if we're multiplying like bases, but if we are dividing like bases. So let's look at number 12. It says use the table to help verify the patterns we noticed previously. Well, we're going to find our own patterns here. First, write each quotient in the table below in expanded form. So just like before, what we're going to do is we now have a problem where we're not multiplying like bases, we're dividing. So this dividing piece is key right here. So what we're going to do in expanded form, similar to what we did with multiplication, is I'm going to write out 2 to the 5th as 2 times 2 times 2 times 2 times 2. And I'm going to write out 2 to the 2nd as 2 times 2. What we're going to realize in something that we notice is that if we have the same number in the top and bottom in a fraction, we know that that same number divided by itself will always be 1. Essentially, it's going to cancel on out because we know if we multiply something by 1, it's still going to be itself. So that's why here they crossed out the 2's. So they crossed out those 2's, a pair of 2's that we have right here. We have another pair of 2's, one on top and bottom, which is why they crossed out the 2's there. Right, crossing them out means we're dividing it out. It's just timesing by 2. So now looking at what we have left, we have 2 times 2 times 2, which is 2 to the 3rd. So I want you to go ahead and try this example out right on the second problem and pause the video. All right, let's go ahead and go over this. Now, instead of rewriting this out twice, I just rewrote it out once. I like to highlight the pairs. Some of you might like crossing them off better. That's fine. But what I realize is that for the pairs, I see, what is it? I see 6 5's on top and 6 5's on bottom. So I know that they cancel each other out since 5 divided by 5 is 1, and multiplying by 1 is not going to change our answer. So I'm left with 5 to the 2nd on top. I want you to go ahead and now try it with the next 2 problems. So stop the video right here, pause it, and go ahead and try these 2 problems. All right, let's go ahead and check. You should have gotten a to the 2nd. And then the reason I use the highlighting is it's kind of hard to cross out x's on the 4th one. So I got x to the 4th. So, okay, now we have to make some observations of patterns. Now, don't look at the expanded form. Ignore this. Think of how we got from this original quotient to our single power. Think of how we got from our original quotient to our single power. And see if you notice that same pattern for each of the problems. So see if you notice. What do we notice about the exponents? How we got to our new result. So what we're going to see is that if I'm given, let's say 7 and 3, when I'm dividing with like bases, what I end up doing is I end up subtracting the exponents. So I keep the same base and I subtract the exponents. So looking at number 3, it says based on the pattern, we observed above, what we're going to do is, we are going to fill in, right, this missing exponent in the box below. We have now a new rule. It's called the quotient of powers property. So again, if you're not keen on the names, it's still good to know the rules that whenever you encounter like bases and you're dividing, what we do is we subtract the exponents. So I'm going to go ahead, I'm going to zoom in a little bit, and I'm going to write in, okay, if I have m divided by n and the both bases are a, we're going to do a to the n minus n. So m minus n, it's always top minus bottom. And we have to remember our base cannot be 0. A will not be 0. We're never going to divide by 0 on the bottom. So let's write out in words this rule. Let's write out in words what this rule is. All right, so we're going to say when you divide like bases, then you subtract the exponents. Nice. So guess what? We just learned another rule. Bam! All right, so we're going to test our knowledge. We're going to go ahead and try number 14, just like last time. Ugh, fractions aren't that scary. All right, don't be afraid. I want you to try to use this rule above. See if you can pause the video right now and try this problem. All right, let's go ahead and talk about this problem. We can see as we're dividing like bases, we subtract the exponents. They both have the same denominator as our fractions, so I can subtract the numbers on top and keep the same bottom. 9 divided by 3 is 3, so we have a to the third. Now, an important piece to look at as when we're doing this is that our base is now in the numerator. I know it's kind of hard to see that from this problem right here because it kind of looks like it's in the middle, but we always, right now, we always move that base to the numerator. Okay, we're going to learn in the future what happens with negative exponents and how that affects numerator and denominator change, but I just wanted to point that out right now. All right, we just made it to the end game. Woohoo! So now that we've learned these rules, we're going to learn how to make the problems a little bit more complex when we're multiplying. We're not just going to have the same base. Maybe we're going to add in some numbers along with some variables. So let's go ahead and take a look at example A below on page 289. So now, looking at this problem, it wants us to simplify this, where we have 2x to the 5th times 5x to the 4th. Well, keep in mind, this is the same, let's get my pen out. This is the same as 2 times x to the 5th times 5 times x to the 4th. Just because there's not time signs in between here, we still know that means times, right? So even though there's just one time sign, they still are all held together by multiplication. So we know with multiplication, we can actually multiply in a different order and still get the same results. So looking at just our plain numbers, we have 2 and 5. So if I reordered this, I could say 2 times 5 first. After that, I know I have x to the 5th and x to the 4th. So I could also say times x to the 5th times x to the 4th. So we can section them off and say 2 times 5. I know that way I get 10. And I can do x to the 5th times x to the 4th. That applies that exponent rule, right, where I add the exponents, right, because it's the same basis. X doesn't magically change into something else. It's still x, but 5 plus 4 will give me 9. So looking at what we just did, that's exactly what they did below, explaining how they use the product of powers property and they simplified our exponent. So that's exactly what we got. So make sure you have written this down, that you're familiar with this, because trust me, it's going to take a step up from here. Let's go ahead and turn to the next and last page, 290. All right, looking at this, we're going to have a more complex example looking at example B, where now, wow, we have multiple bases, x and y, and guess what? We're dividing. Woo! Okay, so let's start talking this out, all right? So we talked about before how we know in the numerator, it's still 2 times x to the 5th times y to the 4th. They're all held together by multiplication, even if the time signs aren't there. We know in our denominator, we have x times y to the 2nd. Now, as a reminder, if we just have a variable by itself, we know the exponent is 1. So I always like to put a little 1 there just to remind me that x to, a power that isn't there is always x to the 1st. It's kind of like when we write 1x, it's the same thing as x. We know x is going to be the same as x to the 1st. So just kind of, a food for thought idea to keep in mind over here. All right, so idea. Keep that in mind. Write that down in the margin. All right, so not getting sidetracked, going back to example B. Okay, so now let's start to look at this. What we're going to do is we're going to group different bases together that are alike. So I'm going to use my handy dandy colors, and I'm going to look and see, hey, in the numerator and denominator, I have the same base of x. I also see I have the same base of y. So I'm going to use my colors to kind of segment them together. Lo and behold, even though there's only a number in the top, we know that technically looking at this, that there is a number in our denominator. Even if we don't have a number there, it's 1. So technically, I will say we do have a number in the top and bottom, but we know it's not going to make a difference. But still, I'm going to group them together just to show you, what's going on. So I'll group the 2 and the 1 together. Okay, so now moving forward, looking at this, we can actually go ahead and apply our exponent rules when we have actual exponents. So we know for the x and the y, we're going to use our exponent rules of, when we divide like bases, we're going to subtract the exponents. So keep in mind, we're going to have x to the 5 minus 1 on top. Remember, we move that base to the top. It always goes up to the top. Same with our y values. We're going to have y on top, so it's going to be y minus 2. Sorry, 4 minus 2. I was looking at the y. All this is in the numerator. Now, looking at the 2 and the 1, those are numbers, normal numbers. They are not exponents, right? We're going to learn a word for those. These are actually coefficients. They're numbers in front of our variable bases. But we can actually apply normal number rules to these because there's no exponents that we see. So we can actually do 2 divided by 1. We don't do subtraction, right? That's only with the exponent rules, right? That's why I made it very clear. These are just exponent rules. But we can divide 2 by 1, and that gives us 2. So we're still multiplying all of these together. We're still multiplying 2 times, 5 minus 1 is x to the 4th. And, y to the 4 minus 2 is going to be y to the 2nd. So these are all multiplied there. You can have that multiplication symbol, or you could actually delete that multiplication symbol throughout all of those. It doesn't really matter. The answer is accepted either way. If you wanted to put it this way, or if you wanted to say 2x to the 4th, y to the 2nd, a lot of times you'll see it kind of the latter way, just because it's a little bit easier to know, hey, we're still multiplying them all together even though we don't have the multiplication sign. And that's exactly what they got here. So I know we've learned a lot today, but you've been doing such a great job of taking notes, of pausing the video and practicing problems on your own. Right now, here is where you're going to check your teacher's calendar. You're going to check in with your teacher to see what your homework is for tonight. Now, Miss Graham's class, our homework for tonight is I want you to go ahead and complete the try these A through B. So we are on page, again, this is page 290, and I want you to do the try these A through B. I want you to do part A, B, and C. I want you to go ahead and test all of those out. All right, so you're going to go ahead and try all of those tonight. So have fun mathing. Enjoy your first math lesson coming back from winter break, and we look forward to seeing you tomorrow.